Hello and welcome to today's physics class. For this class, we'll look at the concept of stress, strain, and Young's modulus. We'll look at these three concepts and their mathematical expressions and their definition, also their unit. By the way, we also look at how to solve several past questions based on JAMB and WAEC and perhaps little of institutional past questions on the concept of stress, strain, and Young's modulus. Let's start the first one there called stress. Let's start the first one there called stress. All right. By definition, stress can be defined as the force acting per unit area of a material. So I'm saying that stress is simply the ratio of force to its area of a material. Note that stress is represented by a Greek symbol called sigma. So we use a Greek symbol, this sigma, to represent stress. So I'm saying that stress is simply the force acting per unit area of a material is represented by a Greek symbol called sigma. So at this point now, mathematically, stress sigma is equal to what? Force all over area. So note that the mathematical expression of stress becomes force all over area. Let's get the SI unit. Of course, force is measured in Newton, area in meter squared. So I'm saying that the SI unit for stress is given to be what? Newton per meter square, or you call it what? Pascal. So either you call it Newton per meter square or Pascal. Anyone, if you want to, they are still very much correct. So PA, Pascal per se. So I have this here. So the SI unit for stress is what? Newton per meter squared. Very important, please. Not very important, please. So it becomes the whole concept behind stress. So force over area, Newton per meter squared as its SI unit. Let's look at the second concept called strain. Let's look at strain. All right. By definition, let's look at strain. Its definition and its mathematical representation. What's strain by definition? Strain can be defined as the ratio of elongation or deformation to its original length of a material. So I'm saying when it comes to strain, it's simply the ratio of elongation or deformation of a material to its original length, right? So I'm saying that by the way, strain is represented by a Greek symbol called epsilon. So we use this symbol to represent strain. Epsilon is simply a Greek symbol used for representing strain. So at this point now, mathematically, I'm saying that strain is equal to what? Deformation, or perhaps I can use what? Extension, if you want to. Either use deformation or use extension all over what? The original length. So by the way, when it comes to strain, there is that I'm taking the ratio of a length over another length. Look at the word I'm using, deformation. Either I call it deformation what or extension, anyone you want to use. So deformation is, of course, is measured in meter. Original length, of course, also in meter. Meter cancel meter. So note that strain has no SI unit, please. So very important. So note that strain has no SI unit. So I have this one here. So having a look at the concept of strain and stress and strain, let's look at one last thing called Young's modulus and we'll solve several past questions. Let's look at the third concept there called Young's modulus. So look at the concept of Young's modulus. All right. By definition, Young's modulus is also called modulus of elasticity, right? It's simply the ratio of stress to strain of a material. So when it comes to Young modulus, the symbol for representing modulus is what? Is E. We use capital E to represent Young's modulus. So now mathematically, Young modulus E is equal to what? Stress all over what? The strain, where stress is sigma and where strain is what? Epsilon. So I'm saying that Young modulus E is equal to what? Stress over what? Over strain. So that becomes my SI unit, sorry, my mathematical expression for Young's modulus. By the way, we said stress is better than what? In Newton per meter squared over extension has no unit. So it has no unit, right? So let's say over 1. So I'm saying that now, this divided by this will still give me what? Newton per meter squared. So I'm saying that Young modulus, so the SI unit for Young modulus is given as what? Newton per meter squared. So note that Young modulus and stress has the same SI unit. Of course, Newton per meter squared. So I'm having what there? Newton per meter squared at this point here too. So this becomes your concept behind Young's modulus. So there are other formulas for calculating Young's modulus aside from stress over strain. Let's do some derivation of the other formula for calculating Young's modulus. Recall that we said Young's modulus E is what? Stress over strain. But what's stress? Force over area all over what's strain? Extension over what? Original length or deformation over original length. Let's do this way. For me, I'll have force all over area. This is divided by extension over length. From here, Young modulus E is equal to F over A, that is this. So change the division to times L converse over what? Extension. Combine this, I can also express Young modulus as the product of what? Force and length to each what? The area and extension. So this becomes another mathematical expression for calculating Young's modulus. So this becomes yet another expression for calculating Young's modulus. Force times length all over area times extension, or perhaps deformation if you want to. With this few concepts here, let's look at several JAMB and WAEC past questions and let's see what we get. Welcome back. The example here says, given that a load of 15 kg extends an elastic material of length 12 meter by 12 centimeter, if the cross-sectional area, if the cross-section of the elastic material is 0.35 meters squared, find number 1, force constant, number 2, stress, 3, strain, and number 4, Young's modulus. So how do you get this done? Very first thing here is quite simple. My very first task here is to list out the givens. So solution here, what are we given? So very first thing in science, list out the given parameters. So given that a load of 15 kilogram, that's my load, that's my force per se. So I'm giving force to be what, the F to be 15 kilogram. But by the way, force is not in kilogram, perhaps in Newton. So at this point I'll say that force is what, mass times gravity, right? So force now is what's my mass, that's 15, times gravity is 9.8. So I want to my task line is that I want to convert kilogram to Newton. By the way, force is never in kilogram. So convert this kilogram to Newton. I'll multiply by what? By what? 9.8 or 10 if you want to. So if I multiply by 9.8, my force now will be equal in value to 147 Newton after conversion. So the idea is that to convert kilogram to Newton, just multiply by 10 or use 9.8, anyone if you want to. In this case here, I choose to use 9.8. So I have this value for my force. All right, let's continue. Extend an elastic material of length 12 meter. So I have my length there, 12 meter. So length, that's L, has been 12 meters. By the way, our length are usually in meters, so I have meter, no conversion. Next up, 12 meter by 12 centimeter. So observe that I'm given the length, original length as 12 meter, and I'm also given another length. That length becomes what? An extension, right? And what? An extension. So I'm given extension E. Extension, that is E, as what? As 12 centimeter. Please. So the extension given in the question is simply 12 centimeter. I'll simply convert the centimeter to meter. So I have 0.12 meters because we said extension are usually in meters. So I have meters there. I'm also given the area, right, to be 0.35 meters squared, right? So sorry, I have actually done the video of all this, but because my camera has actually went off, so I didn't know. So I can't just write this. Just have to explain why I got to this. So I have my area as being this value here. So my very first question says find the what? Force constant. And last class when we discussed about the concept of Oakes law, we said Oakes law gives us the idea that force is what? Ke. And I said this K is called, I emphasize on this. I say K is what? Is spring constant or force constant. So I'm not looking for force constant, that's K. So I have K here. But mathematically, we said, recall that for me, if I make K subject, K will be equal to what? F over E. What's F? Of course, your force is 147 as here, over E is extension as being 0.12. Divide this 2, I'll have this as my answer. Perhaps note that K, last slide we said, is measured in what? Newton per meter. So I have Newton per meter as my S sign here. So that's my very first question I'm told to calculate for. Number 2 says that calculate for stress. Well, we know that stress is what? Force over area, as discussed earlier. What's force there? Of course, my force is what? 147, which I have here. What's area? Of course, area is 0.35 meters squared. I have this here. Divide these 2, I'll have my stress to be equal to 420 Newton per meter squared. So I have this as my value for stress. Third question says calculate for what? Strain. Recall that we said strain is what? Extension or deformation over what? Original length. When I give you the expression, I use the word deformation. But in this question here, we're given extension, so I'll use the word extension over what? Original length. What's extension? That's what? 0.12. What's original length there? Original length is 12 meters. So divide this 2, I'll have 0.01. Of course, we said strain has no SI unit. Please don't put meter here. It has no SI in place. No SI in place. The last one says calculate what? Newton's modulus. And that's what? Stress over strain, as discussed earlier. What's your stress? Stress is what? 4202 over strain, that's 0.01. So I have this. So my stress becomes, divide this 2, I'll have this as my answer. Right? So mind you, I have 42000 Newton per meter squared as my answer. But I just said that kilo is 10 to the power 3, mega 10 to the power 6, giga 10 to the power 9, tera 10 to the power 12. So I'm saying these three zeros here, I can represent as what? As kilo. So I have 4242. This as what? Kilo Newton per meter square. So this becomes my answer to this particular problem. So we'll look at next class, look at other concepts ranging from the work done in a spring. So see you next class. Do well to like this video, share to your friends, subscribe to my channel please. I really need subscribers. Please subscribe to my channel. So thank you for watching and welcome to Excellent Link Academy.